Welcome to this tutorial, and today we're going to be looking at how we create an Arduino project. What we're going to be looking at is how the code is designed, and then we're going to look especially at a thing called task switching. Many people, when they first start with the Arduino, what they tend to do is go and pick up some code samples and then try and stick those code samples together, and of course things initially go well, and then you start to get yourself into a bit of a sticky situation and things start to go wrong. So what we're going to do today is look at how you would design a project from the ground up. Now, before we get started, let's just define what I mean by a project. So if I just switch over my screens a second. Here you have the Arduino Blink sketch. It's been slightly modified for something I'm going to look at later, but it's not really a project in that it's using a single component and it's just turning that single component on and off. When I'm talking about projects, I'm talking about things where we start to use multiple sensors, buttons, inputs, outputs, where we're mixing a lot of different things together. So actually building something that's quite useful. Today, as the example, we are going to be looking at building a bit of an alarm system, but the principles we'll learn today would be true for anything. You know, the same thing would work if you were building a robot car, an irrigation system, a weather station. And very often when people have looked at some of the projects I've built, they sort of think, well, how on earth do you figure out how to put all that stuff together? So even for complex projects, the principles we'll learn today are the principles that we would apply. So let's get started and get straight into how our projects work. So looking at this empty sketch, a lot of work to be done. The setup area, for those who know how Arduinos work, is basically a set of code that only runs once. Then what we do is we have a set of code in the main loop that runs repeatedly. And that's the main area that we're going to focus on today. So let's look at this little example I've built. This is what I would call linear code. Now we're building an alarm system. So we're going to have a PIR sensor. So this is one of those little white sensors. You'll see them under automatic lights and things like that. It detects movement. And for this one, when it detects movement, it's going to set an alarm off if we don't enter a code into the keypad. So if we can think of our linear code, we're tending to think that these items are going to happen one after another. But as you start to think about your project, and this is why very often projects start to get out of hand, these items don't actually necessarily happen in this order. The sensor picks up some movement. Now, that doesn't mean that we necessarily go straight to the keypad next, because if someone doesn't put anything in the keypad, we might want the alarm to come on. At the same time, if they are putting the code in slow, they might just be messing us about, trying to hoax the system. We may want the alarm to come on anyway. We may want the alarm to come on if they put a wrong code in. We may want the alarm to start giving a warning that they've got to put something in and be sounding while they're putting things into the keypad. So as things like that happen, the code starts to fail if we are building in a linear format. The same would happen with a car. If we're building an obstacle avoidance car, we could start the car moving. We then have the sensor, but we actually want the sensor and the moving or stopping to be going on at the same time. We want both items running at the same time, and in a linear format that doesn't work. So what we need to do is go down to a thing called task switching. And what task switching does is it allows a bit of everything to be happening at the same time. So in a task switching alarm system, the PIR sensor is being checked all the time. The keypad is being checked all the time, and the alarm also can be triggered or not triggered all of the time. Now, if you'll notice, my boxes aren't directly in line, and that's because when we're task switching, not everything is happening at exactly the same time. There is actually a very slight time lag between different items. The problem is, for us as human beings, we often struggle to understand just how fast an Arduino is working. So your Arduino is 16 megahertz, which means it can process an instruction in 0.00000000625 of a second. That is a crazy fraction of time. We're talking, basically down into the below a millionth of a second. So when we think about getting a keypad input, we tend to think about the button is being pressed, but actually when you press that button, no matter how fast your ninja reflexes are, you're actually going to be pressing that button for a considerable amount of time. If you consider that when you blink, it takes about, if you blink really fast, it takes about 0.1 of a second. Now, if you can imagine, if I said to you, could you press a button and release it in 0.1 of a second? Could you do it quicker than you could blink? In all honesty, the answer is no. So although you might think, well, we've got to wait for an instant input, we basically have about 0.1 of a second in which time we can check the keypad. So the way task switching works is that we check the PIR sensor, we check the keypad, we check the alarm status. Let's face it, the PIR sensor we want to check for movement. Do we need to check for movement every millisecond? Of course not. People aren't that fast unless you've got a superhero flying by who can sort of go at warp speed. Even someone running really, really fast is not going to get past your sensor in less than 0.1 of a second. So as long as you checked that sensor every 0.01 of a second, you're guaranteed to pick them up as they go by. And so what task switching allows us to do is check the different components, not quite simultaneously, but checking them in a way that feels like everything is happening at the same time. If you're using an older computer, modern computers can actually technically multitask, but when I first started programming, there were no multitasking processors, and your computer is a good example of task switching. If you can imagine, even at your most basic computer, you've got a keyboard and a mouse, and if we go back to our code loop here, if you were programming a really old-fashioned computer, in your loop here you would have a bit of code here that said keyboard. Below that you'd have mouse. Often under that you'd have window system. That's not the operating system, that's the way that you would have controlled the windows within the computer that you were operating. And then further on you would have various other outputs, and each of these items needed to be checked very, very quickly, because there may be a keyboard input, there may not, there may be a mouse input, there may not. So all of these things would need to be checked very, very quickly. And that's what we're going to look at today as we design our alarm code. We're going to look at how do we design the system that everything gets checked constantly but works in the order that we want it to work in without tons of control code. So as we start to think about our project, we've got a PIR sensor, the keyboard and the alarm. Let's now have a look at designing some code and start to think about what needs to happen. So within my particular system, I've done them in a bit of an odd way, but you'll see why. I started by designing the alarms. Now I decided I wanted two different types of alarm. I wanted one that would be the alarm that would go on to say someone's breaking into the house, but I also wanted just a little reminder sound to let someone know that they need to enter the code into the keypad. So to build this, I'm going to have a buzzer and I'm going to have an LED that flashes on and off. Now, if we think about our Arduino, we can process something like 16 million instructions per second, and to turn the LED on and off is going to take less than 1/1,000,000th of a second. So if we think about it, just turning that LED on and off is not exactly hard work for the Arduino. I've then got the PIR timer code that I'm going to write. Now you'll notice I've got millis in here. So if I'm turning the LED on and off, I'm going to turn it on and off at alarm state once a second, a bit like the blink state, the old blink sketch. So I only need to, if you like, use a few cycles of processor power every second. My PIR timer, again I'm going to use millis, but I'm going to check it every 0.1 of a second. Again, I'm going to use up very little processing time. My Arduino is still doing very little. I'm then going to have a control function that will actually control how the alarm works, and you'll see this all in the code a little bit later. Again, it'll use various timers, so it won't use up much code. And then I'm going to have one function that doesn't have a timer, which is going to be the keyboard input. And I just don't need to have a timer because it can use up all the space that everything else isn't using. So that's how I'm going to design the code. Now, as I said, the first bit that I'm going to start with is the LED and buzzers. Very often what people try to do when they build a project is they try to build everything in one go. What I tend to do is I will think, okay, I need a buzzer and an LED that I want to do various things with. I will build those as a separate sketch. Then I'll build a separate sketch for the PIR sensor, the keyboard input, and I'll make sure that I understand fully how each individual item works, and then I can put the code together. So let's work through the sketches and see how this project will be built. So this is the first sketch, and I've called it Alarm LED version 1. Thankfully I managed to do it in one go. I'm one of these people who will have a go at something, and then if I make a certain number of modifications, I'll create a version 2 and keep doing that so that when I make a major blunder, I can go back to the last working version. So on this, first thing I do is list the pins that I'm going to use. I've got a buzzer on pin 11, and I'm using the built-in LED for this example, so I'm using pin 13. Again, I don't use the name, sort of the built-in LED function itself. Is it LED built-in or built-in LED? Forget which one it is. I don't tend to use that because on certain types of board I use the LED is on a completely different pin and that function doesn't work. So I declare the pin as pin 13. I've got a buzzer pin that's pin 11. In the setup, I start the serial. I do that because up here I can now see that I have got this sketch loaded correctly, and then I've got the buzzer and the LED both declared as outputs. Now let's think about what I'm trying to accomplish here. I decided that I want, first of all, an alarm. So the alarm is obviously the noise that it makes when the system thinks someone's breaking in. And then I've got another function here, my warn, which is a warning to someone to enter their passcode. So a bit like a countdown. You know, I have to open a building at the weekend, and when you open that building, there's a sort of a bleeper starts to sound to say, if you don't turn the alarm off in the next 5 seconds, it'll be calling the police. And that's what I wanted as the warning system. So let's have a look at the two functions that have been created. So let's just scroll that down a little bit further so you can see some more. Right. So the first thing with all of these things, because we're going to be linking this with some other components, not only do I need this to work in a function, hence the reason for putting this here, but I need a very, very simple system to turn the alarm on and off. And so what I've created is an integer here, sound alarm. If the value is 0, the alarm doesn't sound. If the value is 1, the alarm goes off. I've then got something called alarm state that you'll see how it works within the code. I've got a timer because I need to use millis, and I've got an alarm delay. So let's have a look at how this particular function works. First of all, it says, is sound alarm greater than 0? In other words, is it a 1? Do I need to sound the alarm? If that value isn't greater than 0, it won't even go through the rest of the function. It just leaves. Now, if you can imagine, that has just saved huge amounts of processing time. It's probably used about 3 clock cycles to check that particular item. So it's done that in an absolute fraction of a second. However, if the system is set to sound an alarm, the next thing it does is it says, is it time for me to do anything? Because we're using a timer here. So it will only actually process code in here if a certain period of time, which in this case is 1000 milliseconds, 1 second, has gone by. If that time period hasn't gone by, yet again, it exits the function, saves a whole load of clock time, and gets on with something else. So if the period of time has gone by and the alarm is due to be sounded, the first thing we do is we reset the value for the alarm timer. So we're going to set it to millis, which is the number of milliseconds since the Arduino was turned on, plus a delay, which is 1 second. So I'm going to set it for 1 second in the future. And then we're going to check the value of alarm state, which is a variable we had up here. And what it's saying is, if alarm state is smaller than 1, set it to 1. And then, of course, if it isn't, if it's greater than 1 or greater than 0, sorry, if it's equal to 1, set it to 0. Crumbs, it takes to get your head around this stuff at times. And then what it does is, on 1 cycle, it sets the LED pin high, starts the sound, the light, and I've got a little buzzer, and it uses the tone function to create a sound. 1 second later, it then turns the LED off, and it turns the buzzer to a different tone. So basically, it sounds a bit like a police car, a real lousy sounding police car, and the LED is flashing on and off. That's my alarm system. You could have connected this, instead of it sending an LED pin high, it could have been a relay pin that was suddenly turning sort of bigger lights on and off, or more flashing lights, or dialing a number, doing anything you want. You know, on my cat washer system, when the cat gets detected, this flips an LED and the cat gets squirted with water. It's detected movement. So this bit of code can be whatever you want, but for this example, I've just used a buzzer and I'm flashing the built-in LED on and off. So that's how I'm going to have my alarm system. So all I need to do later on in my code, and for testing purposes, if I change that value to 1, then obviously this function will run and sound the alarm. I've got it set to 0 because I've been able to test this. I know that it now works. I've done exactly the same then with the other function, which is the warning system. Again, I've got the integer sound warning, 0 it's off, 1 the warning tone should sound. Warn state is very similar to alarm state. It tells me if I'm on the on or off cycle. And I've got a timer. Now you'll notice in this thing I don't have the alarm delay, and you'll see why. So first of all, obviously we're going to check, do I need to sound the warning sound? Is it greater than 0? If it is, deal with the timer. And you'll notice I don't reset the timer immediately afterwards. What it does here is if the value is smaller than 1, it sets warning state to 1. It puts the LED high. It sets the buzzer to set a tone. And then what it does is it sets the timer for 0.1 of a second into the future. So I only want the LED just to flash on and for this buzzer just to sound a very quick bleep. The alternate state, it turns the LED off, and it uses no tone to turn the buzzer off, and this time it adds 500 milliseconds, half a second. So what this is doing is it's bleeping for 0.1 of a second, and then it's silent for half a second. So the idea is that that is going on while the person is putting in their key code. So that's the first sketch, and again these have been written independently, they've been tested independently, and of course now I know that they work, I know that they're safe to put in with my other code. So let's get on with the next sketch. So the next sketch is just checking that I understand how the keypad works. Now when you load the library keypad in your library management system, you will then get some examples, and in the keypad example, he says, looking down, where is keypad? There we go, keypad. You've got various examples in there. I think the example this is based on is the custom keypad one, but it's altered for the pins that I want to use. Now you'll notice once again I have listed the pins. I'm using pins 2 to 9. Now on this project this is getting quite important. I'm using one of those very basic sort of floppy keypads that you often get with the Arduino starter kits. It's a 4x4 keypad, so it's got 8 pins that it requires off the Arduino. So by the time we've added the PIR sensor and an LED and a buzzer, it's quite important to keep track of all the pins that you're using, because otherwise you're going to be trying to use the same pin twice. And that's why in all my sketches I list the pins that this particular sketch is using. Now this is a very basic setup. Again, all this code is on the Digital Town website, so there'll be a link below the video so you can check the code out anytime. But basically all this does, it's a very basic sketch, and all I'm doing is checking that when I press a button on the keypad, it serial prints the value of that button into the serial monitor. Just load this up. He says, waiting patiently. So now I should be able to, there we go. As I press the different buttons on my keypad, they're all coming up, including the symbols and stuff. So I now know that the keypad connections that I've got here are all working. So the final component, now that we've done the keypad and we've sort of done the LED and the buzzer, is the PIR, the movement detector. So let's have a quick look at this sketch. So again, I've got my pin 12 that I'm using here. So the PIR pin is there. I've got an integer called my movement, an unsigned long, which is the timer, and then I've got another integer, my scan delay. You'll start to see that the same types of code get repeated over and over again. Then in the main loop, all I've got is my function PIR scan. Obviously in the setup, I put my PIR pin as an input. And then here's the function. So again, we see if millis is greater than the PIR timer. If it is, I add the PIR scan delay value to the current time. So basically I'm setting this to trigger every 0.1 of a second. And then what it's doing is just reading the digital pin to get the value, and then it's printing that out. And as you look on the side, I've got a series of zeros, and now if I do some movement, we get a 1. Because the way I've got my PIR sensor set up, it'll now take a little bit of time before that goes back to 0. But now we have a simple function that is checking the PIR sensor every 0.1 of a second. So now that we've got all the individual components working, now we can start to put this together. And this same methodology, you would use it whether you were building a robot car. I've just built an oscilloscope. I used exactly the same method here, testing out each component. When I've built big sort of model railway controllers, it's a similar thing. I work out how to control each individual component, and then I put the components together. The other great thing about doing this as an individual component is that I save all of these out. You'll notice this is PIR version 2. I've got that in a folder for my sketches to do with PIR sensors, and that means next time I want to use a PIR sensor, I know that I can go into that folder and I can pick out a piece of code that's going to work first time. So now that we've got the different items, let's look at how we start to put the code together. Now in this sketch, what we're going to do is put together the LED buzzer sketch with the PIR sensor. Now I'll be honest, this is a pretty simple system. If I was doing this normally with the experience I'd got, I'd have put the whole thing together in one go. But when I'm building bigger projects, this is the methodology that I use, and I'll put a couple of items together, get them working well together, and then start to add in the next item. So we know from our previous sketches, we've created a function called PIR scan, we've had my alarm, and we've had my warn, and you'll notice now we have a new function called alarm control. As usual, I've declared all the pins in my header. They're all listed. The only difference that I've tended to do in this sketch that I wouldn't do in my own sketches is that above each function I've left the variables for that function right above the function. What I tend to do is put them further up in the sketch in one section, although even then I would give them, I would sort of put something like alarm variables and then later on the PIR variables. So I do that sort of thing so that I know which variables belong where. But you'll notice I also, when I'm doing something for the alarm, I've tried to make sure that the word alarm is in that variable name. So this function hasn't been altered. We've got the warning function, again, hasn't been altered. We've got the PIR function, no changes there. So the big change here is all in this new function called alarm control. So what this one does is, if you can remember from the PIR sensor, I have actually commented out one little bit here, I don't need that coming up in the serial monitor all the time, but when we read the PIR pin, it creates a value for my movement. Now that is a global variable because I want to be able to read it in other places. And if you can imagine, the alarm control system, all it needs to keep doing is checking, has there been any movement? If there's been some movement, so if my movement is greater than 0, then obviously we need to do something. If there's been no movement, then we don't need to do anything. So the else statement is the bit that we're going to look at first. So if there is now no movement, let's imagine our system's been triggered by a cat that's walked in front of our alarm. The cat has now wandered off. We don't want to set alarms going all night. We just want the system to turn off. So what it does is, if there is no movement, it just makes sure that no LEDs are lit, the buzzer is turned off, we've turned the sound warning value to 0, we've turned the sound alarm to 0. So basically we're turning the warning off, we're turning the alarm off, and we're setting the control state to 0. And the control state is how we work through the alarm control system. So if we get some movement, someone's walked up to our system, the current control state would be 0, and above here I've put in the control states. So 0, there's no movement; 1, movement with a prompt for the keypad; 2, the alarm sounds; 3, the system disarms. That's the process I'm working through. So if this is a new movement, we immediately set the control state to the next value, 1. We add a value to the millis timer, because the first thing I've got to do is check, is this a legitimate time to check this? I then add this value of 5 seconds. So what this is going to do is we're going to turn the warning sound on, but not the alarm, and we're going to allow that sound to keep playing, because now as the system loops, it's going to keep running through this. Sound warn is going to be greater than 0, so this function is going to keep running, turning the little bleep on and off. But what we're telling the system is we've started the warning, and now we want to jump to the next stage in the process. So what it does is the system waits for the control timer to time out again. So it's going to wait 5 seconds. This time what it's going to do is it is going to actually set the alarm sounding, and it's going to do that for 20 seconds. So it's going to set the control state to 2. The warning sound is going to stop, and instead the alarm is going to sound. And then of course once the alarm is sounding, we then go to state case 2, where the system basically waits for this timer to time out, and then it adds a 10-second break before it goes through the system again. And at that point it set the control state back to 0, and it'll just run through the whole process again if there is any movement, but with a 10-second break to give the neighbours a bit of peace and quiet. You'll notice I've put, if there is any other state that is found, there is going to be an error of an invalid state. Now you will notice that when we looked at the code, there is actually a state for 3 which is disarmed, which at this moment is not in this system, and that's because I haven't got the keypad in, so there's no point putting that part into the code. But what we now have is the ability to link the various the PIR sensor with the 2 different alarms, and we can check that it is running through its correct stages on its own before we enter the add the keypad into the system, which will be the next item. So here we are in version 2, and now we're going to add the keypad. Now once again, now you start to see why the pins need to be listed, because we're starting to work our way through most of the pins. So it's quite important to keep a track of just what is using what. Now I've added the keypad library in, set the keypad up as I've done before. We've got the various buzzer and PIR pins, and as we now go down to our main loop, you can see that we've got our PIR scan that we've done before. We've got alarm control, we've done that, we've done my alarm, we've done my warning, and now we've got a new function called key input. Now, even the best laid plans change, and one of the things I realized was in my code originally I was going to have a case of 3 for disarming the alarm. I didn't actually need it. I found out a more efficient way of writing my code happens, and so I didn't need that extra value. So what we're going to look at is how we're now going to deal with the key presses. So let's have a look at what we've got here. Just to remind myself what's going on, the star key is reset, the hash key is being used as the enter button, and all the other buttons on the keypad are valid values to enter. So the passcode, I'm keeping it in a array, and so my passcode is 123A, just across the top line for testing, much easier. And then I've then created a second array called input code, which will store the actual values that the person has entered. I've got a value here called code length, and you'll see why this comes up a number of times within the code. So if I wanted this to be 5 characters long or 6 characters long, I'd need to change this value, and this value to make sure that they're all the same. I've got an input counter that's checking how many characters the person has actually put in, and then we've got our value for the key that was pressed. Within the function here, I've got one other integer that I've declared as a local value, which is Q, which I use a lot in my counters. So let's have a look at what's going on. So unlike the other functions, there is no millis timer within this function. And the reason is that it's the one function that I'd like to be quite the most responsive, and so it's basically using up all the processor time that isn't being used by the other items. Now, if you were doing a different type of project, you may have a different item that needs priority. So, you know, on a lot of this, we're checking something every 0.1 of a second. On my cat washer project, I have a temperature sensor that is in there to check if the temperature has dropped below a certain value, so that I don't try squirting water when the pump is frozen. Now, living in the UK, it gets cold, but it doesn't get cold that quickly. So realistically, I only need to check that value every 30 seconds. I probably check it every 5 minutes just to be sure. But I've got other projects, for instance, I've got an oscilloscope where I have one particular value that has to be checked 10,000 times a second. So again, depending which item needs to be checked the most, that's the one that, if you like, gets priority in your code. So for this one, I've decided that the key input can have the priority for now, and if the key input causes a slight delay on, let's imagine, somehow because I'm pressing keys, this value is checked a millisecond later than it should do, it's not going to cause any problems to my system. So what we do is we first check, has a key been pressed? If a key hasn't been pressed, it immediately exits the function. There's nothing to do, it just leaves. However, if a key's been pressed, the first thing we've got to see is which key has been pressed. If it's the star key, if you remember, that was the reset button. So if they've pressed the star key, I'm going to put a blank value in all the different slots. So input code Q, so it's from Q to the length of the code, which is a 4-digit code in our case. This is why I've put this as a variable, because it could be changed very easily if I wanted a 5 or 6-digit code. So for all of those values it puts in a blank, and then it puts the input counter to 0, because if I've reset the password then it allows the person to start typing in at the first character again. Now the other code that it immediately checks is this the enter key? So does the person now think that they have put the full code in? I've got a little one here, integer check equals 0. It's another local variable. So what it does is it sets this value to 0. It then works through the full array, checking it against the password array, and if it's not equal, it increments my check. Then what I do is at the end of that, when I've checked all the characters to see if they match, if my check is greater than 0, so one of their characters that they input was wrong, I set the system to control state 1. And control state 1, if you remember from the previous system, means that the alarm is going to start sounding. So I set it to control state 1. I set the control timer to 0. I'm not going to put any time in the millis timer. I want this to happen immediately. And onto my system over here, I just print out invalid code. Now, if you were using an LCD to display this information, you could have that printing out to the LCD to say, hey, you put the wrong code in. If it's the correct code, what it does, and this is why I didn't need the third state in the other function, was I set my movement and give it a value of 0, and then I add 60 seconds to the PIR timer. So now there's no movement. Movement's been set to 0. I've set the PIR timer so the PIR is not even going to check for movement for another minute. This gives someone plenty of time to get into the building. After that, at the same time, I reset the input code. So I put all blanks in and I put the input counter back to 0. So what I've done there is I've left the system ready for someone to enter it again, and the system's just going to shut down for 60 seconds and allow the person in the building. Now, if they've not pressed the star key to reset or the hash key to enter their final password, anything else must just be a character that's being input. So what it does is it inputs the next the character that's been pressed into the input code array. I then increment the input counter so that next time round it'll put it in the next item, and I've actually serial printed out the value that they're putting in, just so that, you know, as I press this I can just check on my system that everything's working correctly. You might wonder what those two X's are for. Well, as I said before, when they reset the code, if I press the reset button, everything goes to blank. So how can I see the blanks? I can't. So I put two X's at the end just so that I can see that there are some blanks in there. So basically what this does is, as you can see, it's slowly allowing the passcode to go in. I'm going to reset the passcode, put some more characters in, and you can slowly see the password building up. Again, if I keep going, you'll notice that it starts to go back to the beginning. So if the input counter gets to greater than 3, it goes back to the start and they'll start entering their code all over again. It just seems to be the way that codes are entered into various things. If you get it wrong, you just go back to the beginning and start again. So that very basically is how the system works. And as you can see, we've slowly added component by component. Everything is now running simultaneously. It's task switching It's not linear code. If we tried to do this in a linear way, it just wouldn't have worked, because we'd have detected movement with the PIR scanner. We'd have then been waiting for someone to put something in with the keyboard, by which time the PIR scanner might not have any more movement, but we've already committed to the key input. It's that sort of thing that just does not work if you write your code in a linear way. You need to run it in a task switching system. The important bit when you're doing task switching is just to have in your mind, how long does it take for someone to do something, and how often does something need to be checked. The things that need to be checked a lot, obviously put the timers smaller. Things that don't have to be checked so often, make the timers longer. And don't be afraid, things like a button, unless they're an absolute ninja, you've got 0.1 of a second to check that value. So if you allow 0.01 of a second and check it every 0.01 of a second, you're always going to get the button that's been pressed. So I hope that's been useful for you. It's been a bit of a long tutorial, but it's trying to get your heads around the way that code needs to task switch, unless you're building the most simple of examples. And it is a problem that most example code you get, because it's only running one component, is always tends to be linear code. And again, once again, you've seen the process. Build each section bit by bit, then stick them all together piece by piece. And again, as you remember, this one is version 2. I'd got version 1, so if I messed up version 2, I can go straight back to version 1 and restart my work again. And that does happen now and again. It does all go wrong. So thanks for watching, and sorry it's been a long one. And if you want any more information, as you can see, there is a link to the Digital Town website on how to create this project. All the code is in there, so you can have a look through it. And don't forget, this type of code is applicable to any project that you do. So thanks for watching, and click the like and subscribe if it's been useful. Bye for now.